Hello everyone, welcome to our free tutoring session. We are starting live right now. So, this is how this works. You guys ask math questions and I answer them. So I have here a board and a pen, and you guys will be able to ask your questions and I'll be able to answer them, and you're going to actually see the answers on the screen. So in a moment I'm actually going to pull up a side screen. It's going to be in this little area, and I'm going to be over there, and we'll be able to work through some math problems together. So I do have a request of like 10 questions so far, but if you have not, if you don't know what Amour Learning is about, please click subscribe now. It should be over here, and you'll be able to see live notifications of when this free tutoring is offered. And post your math questions over here so I can actually answer them. So if you have any math questions at all, you can post them over here. If you have more complex questions that require pictures, please post them below. So what is this about? This is completely free tutoring. My name's Cody Amour. I'm a university math professor, and I'm just trying to offer free tutoring for everyone who's struggling with mathematics at home. And so this is like one of the only free tutoring services out there that you'll find. And I think that because my knowledge of mathematics, I'll be able to help pretty much anyone who comes my way. So please post your math questions over here. And if you're not watching this live, which most of my viewers actually don't, most of my viewers watch me after the live tutoring session, post your math questions below and in the comments section, and I'll actually address them in the next live tutoring session, so you can see your answers posted then. Either way, I'll answer all questions. We actually had a list of 8 questions, as I mentioned in the last previous YouTube live session that I did not get to. I do want to make a comment about it. For one, I unfortunately had to cut the last YouTube live tutoring short and kind of abrupt because there was a dust storm that came over, and unfortunately my power went out for about an hour or two, so I was not able to finish that live tutoring session. But luckily, it looks like the skies are a little bit more clear today, so there shouldn't be a problem. As I said, I really want to give you guys an opportunity to post your questions over here in the live chat while I pull up these questions that I got on my last YouTube live. So while I'm pulling that up, ask your questions. Alrighty, let's see here. So this question is about the Hill Cipher, and I'm gonna I'm not trying to advertise here. I'm really not trying to advertise here. This is an educational resource. If you're looking for cryptography books, I recommend this book by Trapp and Washington. These guys are really good. I personally met Washington. He's really smart. He almost came up with the RSA encryption, but it was actually one of his grad students that did, and that grad student is now very wealthy. So it was pretty cool kind of seeing the guy that advised the creator of RSA encryption. But this question, here we go, I pulled it up, has to do with one crypto or encryption, which is the Hill Cipher. And I was not able to get to last lecture. I wasn't able to get it to the lecture before, so now I'm going to get to that today. Fortunately, it's not letting me pull it up, so let's see if I can get it another way. While we're doing that, again, for those of you who are coming in, make sure you subscribe, make sure you ask questions over here in the live chat. So while this is all loading, do that now. Here we go. We have it. We have our question. So I'm going to pull up the Hill Cipher in here in this textbook to use as a reference, and then we will pull up some examples of the Hill Cipher. And at any point, you can stop me and ask me any math questions you guys want to. Getting there. Here we go. For some reason, not pulling up. Awesome. Okay, so the question has to do with modular arithmetic. This is actually posted by two guys. It's a really good question. So here we go. Again, this is unfortunately really slow. So again, for those of you, we have a question. Can you explain Markov chain Monte Carlo? So the answer is slightly. I can explain what I know, and then we can learn that together. Actually, I know like how Markov chains work and how it relates to linear algebra, and it's basically Markov chains are matrices that allow you to transition from one state to another, and understanding how the states work is something a little different, but I'll get to that in a second because there's a lot of interesting things to say. For now, let me pull up these questions, and then I'll do that right after. For now, let me pull up the Monte Carlo. And then you're about to see the Monte Carlo stuff on the screen here. It's going to be in this position right here. But I first need to close out of this, and then we'll get straight to that. Okay, so let's start with Markov chains, actually, and then we'll get to that. Because it's really important to understand, like, conceptually what a Markov chain is. Let me pull this up. Here we go. Transition. There we go. All right, so hopefully you guys can see this at this point. This is I know this is kind of a Wikipedia page, but we're going to go through it together because unfortunately statistics isn't my forte so much. However, Markov chains are probably one of the only things that that I've looked into a little bit. So let me see if I could find a conceptual understanding here. There's a famous picture for Markov chains I'm looking for. Here we go. Markov chains explained visually. This hopefully will help us out. Okay, so I'm gonna, yeah, I know it. Okay, I'm gonna pull up a whiteboard now, and I'm gonna kind of explain this. So the idea is, and I'm gonna use this pen really to elaborate on this. The idea for Markov chains is that you have these states, they're called. So for example, I have A, I have B, and I have C. And the idea is there's a certain probability that these states will change to different things. So for example, there's a maybe 30% probability that A will go to B. There is a 20% probability that A will go to C. There's a let's say an 80% probability that C will go to B. There's a 10% probability that C will go to A. And let's see here, for B, there is a 40% probability that B will go to C. And there is let's do a 50% probability that B will go to A. So here's the idea of a Markov chain, and this is the basics that I understand it. The idea is these A and B. So first of all, this is widely applicable, extremely applicable, and these decimal numbers represent a probability. Now, let's say we are in A right now. So here we are, and we are going to see what happens. Now, at this point, if you're at A, there's only two paths you can take, this one or this one. Technically, there is a third one, but I don't actually have to explicitly draw it. Because if you notice, there's a 20% probability that we go to C, 30% probability that we go to B. But technically, there's also a third possibility, and it stays at A. And the idea is, if you A to C is 20%, A to B is 50%. Where's the other 50%? What's the if something has to happen, and the total the total probability of all the possible events should add up to 100%. So this actually implies that the probability of A going back to A has to be 50%. For B can go to A with a 50%, a C to 40%, so that's 90% total, which means there's a 10% chance that B will stay where it's at. And then for C can go to B at 80%, C can go to A at 10%, so there's a 10% chance that C will go to itself. And the idea is there is a matrix that we can draw to represent this. So I'm actually going to draw a matrix, and it's a probability matrix. And the way it works, I'm not too familiar with, but this is basically the transition process. And I'm going to explain things a little bit here. But the idea is for the transition matrix is going to be a 3 by 3. The reason is because there are 3 states total, and each row and column is going to represent a transition from one to the other. I believe the way it works is you have your ABC row and your ABC column. And I actually don't think it matters, but I'm pretty sure that this is the rows are the starting positions and the columns are the ending positions. But let me double check that real quick, because that's a really, really important question. And then doesn't seem to have any more other additional questions, but let me get to the matrix here. Ooh, I love this animation. This is pretty cool. Let me look up the transition matrix. Yeah, so I guess it's called the stochastic matrix. I actually didn't know that. I thought they were described as transition matrices. Yeah, it looks like from reading from this, I believe I have the right conception here. Alrighty, so this is how I see it. So yeah, these are your the rows of the starting positions. These guys are my starting positions, and these guys are my ending positions. So here's what the matrix would look like. Starting from A, going to A would be 0.5. Starting from A, going to B would be 0.3. Starting from A, going to C would be 0.2. Starting from B, going to A would be 0.5. Starting from B, going to B would be 0.1. Starting from B, going to C would be 0.4. Starting from C, going to A would be 0.1. C to B would be 0.8. And C to C would be 0.1. So here we have the transition matrix. And we can do a lot of cool things with this. In particular, we can square them to find, for example, what's the probability that if we start at A, what's the probability that we will land at C? So from A to C after, let's say, 5 transitions. Okay, come on, here we go. Transitions. That is not how we spelled it. So the 5 transitions, what's the probability that we're going to go from A to C? And the way we would do that is we would take this matrix, right over here, and we're going to raise it to the 5th power. Basically going to multiply by itself 5 times. Now I actually have a calculator here that's going to do that for me. So first I'm going to, on my graphing calculator, I'm going to go to second and then matrix, and then I'm going to edit the first matrix. This matrix is by 3, kind of probably hard to see from that angle. So let's see, I'm going to write this matrix down. 0.2, 0.5, 0.1, 0.4, 0.1, 0.8, 0.1. Okay. So I have my matrix, and what I'm going to do is I'm going to raise it to the 5th power. So take that matrix, raise it to the 5th power, and I get a new matrix. And I'm actually going to write down this new matrix because it's actually telling of not only the answer to this, but a lot of other, and it answers a lot of other questions as well. So we're going to have a new matrix over here. This matrix is 0.4, and I'm rounding, by the way, rounding to 2 decimal places. 0.35, and then 0.25. Oops. And then we have 0.41. We have 0.34. And then we have 0.25. And then we have 0.39. We have 0.37. And we have 0.24. Okay, so basically what this says is we have, again, our states ABC, ABC, but because we raised it to the 5th power, this is the probability that it starts at A, and then after 5 times it'll end back up at A. So to get from A to C after 5 transitions, that probability is actually right here, 25%. And so that's incredibly useful because, especially if you're in engineering or something like if you're doing some sort of electrical wiring and you're trying to have different states and switches, then this sort of thing is actually incredibly useful if you have a random process involved. Now, what's really cool is what happens. I'm going to kind of go back here a lot. What is really, really awesome is what happens after an infinite number of trials. So I'm actually going to show this. So the question here is what happens as the limit as n goes to infinity. And we'll call this matrix, by the way, we'll call this x. So what is the limit as of x raised to the n power? And you would think that the idea is after an infinite number of times, it's really hard to see where you would end up. So it should be an equal probability that you'd be in A, that you'd be in B, that you'd be in C. But we're going to actually take a look at this particular transition matrix, and I'm going to put a really, really high number here. Instead of 5, I'm going to say what happens after 1,000 transitions. Let's do 100 transitions. So after 100 transitions, it's actually most likely going to be at A. The probability of landing at A, regardless of where you are. If you're at B, if you start at A, if you start at B, if you start at C, the probability of you landing on A is, it looks like 40%. The probability of you landing at B is 35%. And the probability of you landing at C is 25%. So let me explain what I did here. Is I saw what happens after 100 transitions. And the matrix, they're basically the same rows. And the idea is that it doesn't matter where you start from. The probability of landing at A is 40%. The probability of landing at B is 35%. And the probability of landing at C is 25%. So the idea is, chances are you're going to land at A in this example, in this specific example. And that's kind of interesting because Markov chains, you would think after a while of moving around all over the place, you'd kind of land somewhere random. But that's actually not true. You tend to land in certain specific places based off of the Markov chain. Now, I can't really help with the Monte Carlo, but if you have a certain question about this, that I feel like I might not have answered the questions that you had, but if you have a question about this, I might be able to answer more specific questions. So let's see how the comments are doing. Okay, so we have so the follow-up question is the diagonal of the matrix after the limit n approaches infinity x to the n. Oh, good, it was useful. I'm glad. So this is a really good question. The idea is, yeah, the diagonal really tells you what the probability of landing there is. Technically, the idea is, let me write this out a little bit more clearly. I want to actually show you what this matrix looks like real quick. So it's a giant matrix, and this is technically, oh, I have my thing upside down. This is technically x, excuse me, there we go, x to the 100th power, which by the way is relatively large, and it shouldn't change or vary after that point. This is what it looks like. 0.35, uh, 0.25, and what's left over? I said it was 0.4. Is that right? Or actually, sorry, it should be, that 0.4 should be way over here. Let's try that again. So 0.4, 0.35, and then 0.25. There we go. So that's what the first row looks like. The second row is 0.4, 0.35, 0.25. And then the third row is 0.4, 0.35, 0.25. The idea is that the limit as n approaches infinity is you're going to have rows that are all the same. And let me explain what that means. So again, these right here represent, like the row represents where you start from, and the column represents where you end after 100 transitions. So for example, let me use a different color here. This position right here says if you start at B and you transition over to C, after what's the probability of starting at B and transitioning over to C after 100 times? And the answer is 25%. So that's what this 0.25 here represents, is the probability that you start from B and you end up at C after 100 times. But the idea is it doesn't matter where you start. The probability of you landing at A, regardless of where you start, is 40%. The probability of you landing at B, regardless of where you start, is 35%. And the probability of you landing at C, regardless of where you start, is 25%. So what's interesting about Markov chains is that as n approaches infinity, so if you take a look at the limit as n approaches infinity of x to the n, the idea is the rows are the same. And if the rows are the same in a transition matrix, that's another way of saying it doesn't matter where you start. The probability of you ending up at a certain place is whatever it is in that column. So the probability of you landing on A is 40%, C is 25%, B is 35%. And that is really interesting because you would think that it would be 33% across the board in this case. You would think that this is what that matrix would look like. 0.33, 0.33, 0.33, all the way down. You would think that this is what it would look like, because the idea is if you start at A and you move all over the place, you're moving, you're just going to land in a random position. And that's kind of a fair conception because, I mean, when you're moving through when you're taking a look at a Markov chain, it kind of looks like you're flying all over the place, but that's not the case with this Markov chain that we constructed. And it's actually not the case for most Markov chains. So yeah, I challenge you to maybe, if you have like what's the word I'm looking for? A degree that you're studying right now and you're interested in like, how can I apply this? I might be able to tell you like, hey, this is an application of the Markov chains. All right, let's see here. Again, if you guys have, for some reason I wasn't sharing my screen. Let me share my screen real quick and show you what I was drawing. It kind of stinks, I'm sorry. Here we go. So let me just refresh what I just said there. The idea is this is what it looks like. This is what the transition looks like. The columns are all the same because, again, if it doesn't matter where you start, the probability of you landing on A is 40%. If you start at A, the probability of landing at A is 40%. If you start at B, probability of landing at A is 40%. If you start at C, the probability of landing at A is 40%. So that's what I meant by all the rows are the same. And this by the way, this matrix right here just represents what you would think that it would look like, but it's not the case. This is not true, and it rarely is, surprisingly. So sorry about that. I thought I had the screen posted. All right, so it looks like we have a couple viewers. If you guys are interested in posting any math questions, please post your math questions over here. Feel free to subscribe. Click on that subscribe button so that you get notifications. We do free tutoring every Thursday and Sunday at 9 p.m. Eastern Time, which to me is 6 p.m., but this is sort of a free resource that you can use at any point in time. Now, there was one question that I did want to get to from last week, and that is regarding the Hill Cipher. So I'm still trying to pull it up. Let's see if we can do that now. Again, if you guys have any math questions, again, post on the live chat or on the comment section below. Preferably live chat because I'll be able to see that during this video. If you post it on the comments, I'll get to it in the next live tutoring session. Alrighty, so question is about modular arithmetic. We kind of discussed modular arithmetic a little bit in the previous lectures, but this is from, looks like Akash and Shiju. Apologize if I totally botched your name. And there were questions regarding the division algorithm, the extended Euclidean algorithm. So let's see here. We're going to work with modular arithmetic first. I'm going to work with Akash's question first. This is a little bit out of order, and it's pretty much all of number theory in a nutshell. But I'm going to start with the division algorithm because this is the most important algorithm basically in all of mathematics for you guys. So what is the division algorithm? Let's see. Let's take a look at what the division algorithm is. So the idea is that this is basically long division, but without actually using division, which is kind of crazy to think about, because if you're doing long division, you would think you're going to do some division, but this is not the case. So the idea is that if you give me any two numbers, say 720 and we want to divide by, let's say, 3. Yeah, let's do 3. No, let's do 6. Yeah, I like 6. So how does this work? Well, this is going to give a clean number. Let me do 7. That'll work. 7. There we go. So we do 720 divided by 7. How do we do this long division? The idea is we first see how many 7s go into this 7, and the answer is 1. But this is actually not a 1. This is a 100. But we're going to think of it and consider it as 1. And then we're going to multiply 1 times 7, and we're going to subtract that number. So the 7s cancel, and we get a 0. And then we're going to bring down the next number here, 2. 7 does not go into 2, so we put a 0 here, and we bring down this 0. 7 goes into 20 2 times, and that's 2 times 7 is 14. So we're left over with a 6. Now, the division algorithm is pretty straightforward. It basically just says that division works, that when you do that long division works. The idea is when you do long division, you're going to get a quotient and a remainder. So this right here is my quotient, and this right here is the remainder. Now, I'm actually going to rewrite this problem in terms of just multiplication. So this is this whole problem is just like saying 720 is equal to 102 copies of 7 plus an extra remainder of 6. So this is kind of the special way of saying exactly the same thing without using division. So if you notice, there's no division involved. The idea is you can do this with any two numbers, any two integers actually. So the idea is if you give me two integers like, let's say, 81 into 7934682. The idea is I can find a q that goes here, and after a bunch of long division I get an r as my remainder, such that 7934682 is q copies of 81 plus a little bit of a remainder. So we have our quotient and our remainder here. And this can work for any two integers. So it doesn't have to be this giant number right here or 81. It can actually be anything. But I'm going to be more specific here. Basically for any, and this is the division algorithm, for any A and B, and I'm going to let me make B needs to be positive. And these two things, by the way, are integers. That's really important. And it can actually be, A can be negative. So where B is greater than 0, then there exists, that's what this means, and we talked about this in a couple other YouTube live sessions, there actually exists a unique, so that's what this means, a unique Q and R, which are integers as well, such that basically I can do long division between A and B. So A is Q copies of B plus R. But there's actually a restriction on R where R is actually strictly, well, it's actually greater than or equal to 0. It could be 0, it could be no remainder, but it actually has to be strictly less than B, which is why B has to be positive so I can do that. If B was negative, then that last part would be a huge problem. It's actually going to, it would throw off a big proof. And so this is actually a theorem. Now again, if you guys are watching, if you guys just joined in, you can ask any questions on the live chat, and I will interrupt this this particular tutoring session and answer your questions live first. So this is just a question that was asked in the last YouTube live that I did not get to. So I'm going to go over to the live chat real quick and check to see if anyone has any questions. Looks like the answer is no, so we're going to keep going. And again, if you post questions, I'll take a look at all the questions. I'll look at the live chat, I should say, every few minutes. So this is a theorem. This is kind of a unique theorem, and I want to prove it to you guys because it's a brilliant theorem. It's basically stating that no matter what two integers you can give me, I can do the division algorithm. So let's prove it. The first thing we need to do is we need to consider a set of remainders. So first off, this is going to be kind of unique. Let me make sure I get this right. I'm going to create a set R. R is going to be a set. It's actually going to be the set of remainders. And I want the set of remainders that are positive. So if we're talking about, in this case, a divided by b, and the idea is we can create a lot of q's and r's. So for example, if I was doing 7 into 26, there's a lot of different quotients and remainders that I can get. So I could get the quotient 3 with a remainder of 5. So that's possible, but that's not really the only possible quotient and remainder that I could get. I could, in theory, get, for example, 2, a quotient of 2, and a remainder of 12. So this is also a possibility. So I can rewrite this as 26 equals 2 times 7 plus 12. So there are actually infinitely many possibilities for the set of remainders that are positive. At least it looks that way, but we actually have to show that. And to show that, we need to use some tricky proof stuff, some mental gymnastics here for a second. So first off, I just want to show that R is not empty. Because if this is the idea is we're going to play a really unique trick. I'm going to grab a remainder from this and make it the smallest remainder. And then I'm going to play with that remainder for a little bit and prove that it's a unique remainder. But we'll do that later. Let's start with proving that there is a remainder that is positive. I believe if we do R equals the absolute value of, let me see, I want to say A. I'm going to say A times B, the absolute value of A times B. This should always work as a possible remainder. And so let me show you the Q that would get you that. So so if A equals BQ plus R, and by the way, guys, I'm not using a book. I'm going completely ad lib here. That's okay. So R would then mean that this would mean that R is equal to A minus B times Q. And in this case, I'm saying the absolute value of A times B equals A minus B times Q. And so Q would be, this is not going to work. I think it needs to be I'm actually not sure. I think I think we could get away with just the absolute value of A. Let's try that. I think we can get that as a remainder. Actually, I'm going to use that maybe as the quotient. I'm going to pick the quotient to be, this was it, negative absolute value of A. There we go. So this will definitely give me a positive remainder. So if I pick this to be my quotient, I'm definitely going to get a positive remainder. And that way, this would show that R is not the empty set. So if I pick Q to be that, then A equals Q, which is negative absolute value of A, times B, plus R. So R is equal to A plus absolute value of A times B. Now this, by the way, is positive because absolute value of A is positive and B is positive according to what the theorem states. That's an assumption that we made, that B is positive. We don't know A is positive, but we do know B is positive. Now, if B is positive, that means B is greater than 1. So that means I'm taking A, which could be negative. This could be negative, but I'm adding extra copies of A. So if B was 1, for example, that's the lowest number B could be, I would be taking A, which could be negative, and then adding the absolute value of A, which would make it 0. So the idea is if B equals 1, then A plus absolute value of A is greater than or equal to 0. Either this, if A is positive, then a plus the absolute value of a is just 2a, which is positive as well. If a is negative, then this value is negative, but this value is positive, and they cancel each other out, making it equal to 0. So that's what happens if b equals 1. But if b equals 2, or anything above, basically I'm taking a, I'm adding an extra copy of a just to make sure I cancel it out, and then I'm actually adding more copies of a, and an extra copy of a, because this is 2 copies of a. b is 2 now. So I just keep making it more and more positive. So regardless of what b is, and regardless of what a is, r is positive. So we've shown that if q equals negative absolute value of a, r is guaranteed to be at least 0. Which is important, which means that R is not an empty set. And R specifically is a set that has positive integers. And I'm gonna take a quick break. We're gonna go to other questions, but if we don't have any more questions, and you can still ask questions on the live chat way over there, or in the comments section, and I'll address those immediately. This is just a question that was asked last Sunday, but if you guys have any questions, I'll answer those. Let me real quick pull it up. Looks like we still have no questions, which you guys can always ask. There's no problem with that. But let me finish this division algorithm. So again, the idea is R is not the empty set, because if we set the quotient to be negative absolute value of a, regardless of what a and b are, we can find the remainder is forced to be greater than or equal to 0. So R is not empty. So now, that being said, we have R which is the set of remainders. Positive. It should be positive remainders. I only want the positive, and there's actually a reason for that. I don't want negative remainders. The reason is because I'm trying to find not only that there exists a remainder that qualifies for the division algorithm theorem, but also there's a restriction on that remainder that has to be relatively small. So so far we have that R is not empty. So it's not the empty set. So that so right off the bat, because R is a subset of the integers, of the natural numbers actually, and R is not the empty set, by the well-ordering axiom, so well-ordered axiom, this actually means that R has a smallest element. That's awesome. That's great. We have, no matter what, there is a smallest non-negative remainder. And so we should also include here the possibility that 0, because 0 is technically not positive, but whatever. So we have a smallest element for sure, according to the well-ordering axiom. And this remainder is the remainder that we want. So call it R. So we have our smallest non-negative remainder. And I'm going to prove to you that this remainder works. So because there exists a remainder, then there's a corresponding quotient to that, which is great. But we need to prove that this R satisfies this inequality that we put in the theorem itself. Now, it's important to understand that we actually just proved this part. R has to be non-negative simply because it was in that set of non-negative remainders. So that part's easy. We have to show that R is actually less than B, that the smallest remainder is less than B. And the way that we're going to do that is by contradiction. We're going to assume that R is actually greater than or equal to B. And if that happens, we actually run into a problem, because then we have A, which is Q times B plus R. Now, if R is greater than or equal to B, then R minus B has to be greater than or equal to 0. It has to be at least 0. So what I'm going to do is I'm going to write R as B plus some stuff. And there's a problem here that I can actually just take, well, let me subtract B on both sides. R minus B is greater than or equal to 0. But now if I look at A equals, again, I'm doing all this in my head, guys. Q times B plus R, which, by the way, is, I want to say, what I want to do is, oh, this is greater than or equal to Q plus 1 times B minus B. Here's the trick I need to do. So A equals Q times B plus R, which, by the way, is Q plus 1 times B. I'm going to do Q minus 1. I think that's what I want to do. Q minus 1 times B. No, I'm going to add. So Q plus 1 times B minus Q plus R. And so this equals Q plus 1 times B plus R minus Q. Is that what I'm looking for? No? Okay, so it does need to be minus 1. I get it now. So Q minus 1 times B plus R. And if we rewrite this, well, anyways, I can't quite get to this part of the theorem, but there should be a contradiction. I should be able to find a remainder that's smaller, which would contradict. We will get to that on Thursday's lecture. That's okay, though. No problem. If you guys have any questions, please post them over here. If you haven't done so already, make sure you hit the subscribe button. And in the next lecture, we will finish the division algorithm. There's a few just tedious tasks to do from here. And I believe it's just fiddling with that formula. And we will be able to create an inequality to show that we can find a remainder that's even smaller, which would contradict the smallest element, which something that we proved in the well-ordering axiom. I do want to make a couple announcements before we get to the end of this. And again, if you post your math question here, I'll address it. But we will be posting videos now from our statistics course. These are really good videos, really good quality, really good video editing, green screens, but also we have really good lectures that I believe are going to exploit good conceptual understanding, and I think that's really important. So if you guys want to get a head start, I'm going to give you guys a little bit of a sneak preview. We're going to be taking a lot of stuff from Veritasium. So if you haven't checked out his channel, Veritasium is a great YouTube channel to check out. I'm actually going to put it under the featured section of my YouTube channel. That way you guys can just go over to his and subscribe, and that will you'll be able to see some really cool videos from him. So anyways, looks like we still don't have any more math questions, so I'm going to post real quickly a starting in 10 minutes. We're going to take a 10-minute break, and if we don't have any math questions before those 10 minutes end, then we will end today's free math tutoring session. Again, as it says above here, there's free tutoring every Thursday and Sunday at 9 p.m. Eastern time. So please, please, please come by every single time. Share this with your guys' friends. If you know anyone that's struggling in math, please, please, please let them know that this free resource is available to them. Thank you guys so much, and I'll be back in 10 minutes if we have any more questions.